Okay, we're going to be talking about several different trends over the course of this unit. Today we're going to be talking about atomic and ionic radii. So we're going to first make sure we understand what the word trend means. So a trend is the general direction in which something is developing or changing. It doesn't mean it's 100% accurate, it's just the general direction in which something is going. So don't automatically assume that every single element abides by this trend, because otherwise then it wouldn't just be a trend, it would be an absolute. So the periodic table that we currently use in our class was the one that was developed by the Russian chemist Dmitry Mendeleev. He actually started with 63 elements, 63 known elements in 1869, and created a pattern of elements in columns and in rows. The up and down columns he called groups, and the rows across the periodic table he called periods. And he developed the first periodic law and created an article in 1871 that he published called Periodic Regularity of Chemical Elements. So he used these 63 elements and arranged them in columns and rows based on their chemical properties. He did have information from several other scientists over the previous decades about protons, neutrons, electrons, and their atomic masses, as well as different researchers' information about different properties that elements had. But he was the first to create the article. All right, so the radius is what we're going to be talking about today, and that is the measurement from the center of the atom out to the outermost edge. So it's from what we call the nucleus, so the nucleus here in the center, out to the valence electrons. So that's the radius is what we're going to be talking about today. And we're going to talk about atomic radius, and we're going to talk about ionic radius. And they are different things, an atom and an ion. But we're going to see what their trend is today. So the radius is the distance from the center outwards. So let's do a quick review of the parts of the periodic table. The family names you should already know. So these elements, not hydrogen, but lithium through francium, are the alkali metals. Beryllium through radium are the alkaline earth metals. The guys here, that is this short section of the periodic table, are the transition metals. This whole area in general that is here in green, not just the up and down families, are the nonmetals. This column, helium through radon, are the noble gases. This family, fluorine through astatine, are the halogens. If you touch this line, this zigzag line, but you're not aluminum, aluminum's a metal, you are a metalloid. And if you're in this dropout section on the bottom of the periodic table, you are a rare earth metal. Now we have an entire topic from a previous unit on the periodic table families. So if you are not familiar with the periodic table families, you should go back to that PowerPoint to make sure you know all the families of the periodic table. So the trend for atomic size is kind of weird if you think about it. So let's talk about why that is. First of all, it decreases as you go across a period. So let me explain what they're saying. Decreases as it goes across the period. So it means as it goes this way, it's getting smaller. They're saying element number 3, element lithium, is larger than element number 10, neon. Now, why is that? That doesn't really make sense on the surface that element number 3 would be, I'm trying to make a 0 here, not letting me, would be larger than 10. This is what it's saying. It decreases as you go across the period. So to understand that, you have to know that in the center of element number 3 are just 3 protons, and it's got 2 energy levels. And in those energy levels, it has electrons. It's got 1 there one there, one there. So 2 electrons in the innermost energy level and then 1 in the outermost energy level. Now, in the inside of element number 10, now it's got the same number of energy levels. So it's got the same number of energy levels. It doesn't have a different number of energy levels. But on the inside of element number 10, it has 10 protons. That makes the nucleus of number 10 have 10 protons strong. It's 10 protons strong in its nucleus. And this one is only 3 protons strong in its nucleus. So it doesn't have any more energy levels. So when I put in the new electrons in the energy levels, and I'm putting a new electron in every time I get a new proton. So when I put in these 10 electrons, these 10 protons are able to pull them in tighter. It pulls them towards the nucleus because the nucleus of having 10 protons is stronger than the nucleus of only having 3 protons. So it decreases as you go across a period. And it does so because more protons added into the nucleus attract your more electrons that you have placed. So the protons are being added, but you're not getting any more energy levels. They're being added to your nucleus, but they have the same number of energy levels. They're not being added to the energy levels. They're being added to the same number of energy levels. So it tightens the radius of your atom. It pulls it in closer. So every time you get a new proton, your electrons are pulled closer. So your energy levels are pulled in to the nucleus. It has a higher positive charge, which means it has a higher effective nuclear charge. So it increases as you go down a group. This does make sense. So this is kind of harder to think about up here, but this does make perfect sense. It's saying that element number 3, which has only 2 energy levels, is smaller than element number 87, which has 7 energy levels. You can clearly see that this is going to be larger if I have to draw 7 energy levels around here. I can't fit them all, but pretend I did. Okay, so I've got 7 energy levels here. 1, 2, 3, 4, 5, 6. Let's slap another one in there. 7 energy levels. And so one that has only 2 energy levels compared to one that has 7 energy levels, it's getting bigger as you go down. So every time I go down in the same group, every time I go down, I'm going to get larger because I add another energy level. I keep adding another energy level to the elements in that group. And they get bigger then because I add another energy level. There's another factor that's called shield electrons. And shielding electrons are this concept. So I've got just 2 energy levels here. And when I only have 2 energy levels, there are only 2 electrons in the inner energy level when I add this next electron there. But if I had the element underneath that and I had yet another energy level onto here, now I have all of these electrons. Remember, there are 8 electrons in this energy level. And when I add this electron in it, he's got to get pulled into the nucleus. He wants to be attracted to the nucleus because the nucleus, of course, is positive and he's negative. So he wants to be attracted to the nucleus, but all of these negative elements are in the way. So as he is trying to be attracted to the nucleus, all of these electrons in the inner energy levels are shielding him from the positive forces of the nucleus. So the electrons that are in the inner energy levels are called shielding electrons or shield electrons. So here's the overall trend. It increases as you go down because I keep getting new energy levels. So here's my nucleus, and I keep getting a new energy level as I go down the periodic table. I gain another energy level, and of course that increases in size. It decreases as I go to the right. It decreases because every time I gain another proton in my nucleus gets stronger. So every time I gain another nucleus positive force, my nucleus gets stronger. So with every new proton, I get a stronger nucleus. So which is larger, lithium or carbon? So think about the periodic table, grab your periodic table, and let's see where it is on the periodic table. So they're asking me about lithium, which is here, number 3, and carbon, which is in the same family as it, over here. Remember, I decrease as I go this way. So if they're in the same period, lithium is going to be larger. Who is larger, sodium or potassium? So think of the general overview of the periodic table again. Find sodium, find potassium. What happens as you go down the periodic table? As you go down the periodic table, you gain another energy level. When you gain another energy level, you get larger. So who will be larger? Potassium will be larger. Who's larger, boron or beryllium? Find their location on the periodic table and think about the trend. Beryllium is over here and boron is over here. What happens as you go to the right? It gets smaller. That means that beryllium is going to be larger. Okay, so I'm going to let you know I generally overall pick an element that I like to say is my reference element, and I pick an F element because there's an F element on both sides of the periodic table, and the F element that's on both sides of the periodic table that I use as my reference is the element francium. So francium is the largest element, and then up here helium, over here on this side of the periodic table, right there. Helium is the smallest element that's an atom on the periodic table. So the closer you are to francium, the larger you are. So I just use that as my reference element, that the closer I am to francium, and there's an R right there, the closer I am to francium, the larger I am. So if you're just looking at a periodic table and you say bromine or fluorine, which one of them is closer to francium? Well, if you put the elements in, fluorine is up here and bromine is down here. Which one's closer? Whoever is closer is going to be the larger one. So I remember francium is my largest element on the periodic table, and then I only have to know that to understand my trend. So nitrogen or phosphorus, go find nitrogen and phosphorus and see which one's closer to francium, which we've already deemed the largest element on the periodic table. And so you'll see when you go look that up that phosphorus is closer to francium. How about boron or nitrogen? Boron is here and nitrogen is here. Who's closer to francium? And the answer is boron. So here is an illustration that shows you the atomic radii of elements, and you can see that as I go to the right, I am getting smaller. This is the atomic radii for each of the elements on the periodic table. So they're showing you the general trend. You can see that there are a couple elements that don't follow the trend. See, this one is a little bit larger than the one before it. Okay, this one here is larger than the one before it. Okay, so there are a couple outliers, But if you look, you can clearly see that the overall trend is that it gets smaller as you go to the right. Look at the trend as you go down in each of the families or groups. So I get larger as I go down. And francium is the largest element on the periodic table. Okay, so element number 55 is the largest element on the periodic table. So this is the atomic radii of just some general, they're just showing you the overall trend that it gets larger as we go down and smaller as you go to the right. All right, now let's talk about ionic size. And to understand about ionic size, you do have to know the difference between the different types of ions that can be created. So you could either be a cation or an anion. Remember, a cation is a positive ion, and an anion is a negative ion. Cations become positive because they're giving away their electrons. And in some cases, they give enough electrons away to where they don't actually have the whole outermost energy level. So let's look at lithium, for example. When lithium becomes an ion, it starts out here as an atom. Here is lithium as an atom. So when lithium becomes an ion, it's going to become an Li plus 1, which means it's going to give away one of its electrons. When it gives away one of its electrons, it's going to be smaller than it was when it was an atom. If you saw, I just erased an entire energy level, and the element, when it became from an atom to an ion, was smaller. So cations are smaller than their atomic size. So cations get smaller in their atomic size. What do anions do? When anions create ions, they gain electrons. So here, let's make a oxygen. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it's not letting me draw over there. Let's move it over. Okay, so I'm going to make my anion down here. So oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have 8 protons in my nucleus, and I have 8 electrons in my atom. But when I become an anion, I gain more electrons. And when I gain more electrons, now I have only 8 protons. So I only have 8 pluses. So my nuclear positive force is 8. But I have 10 electrons. I kind of think of it as babysitting. If you've got 8 parents at the park watching only 8 kids, everybody only has to watch 1-to-1 ratio. But let's say 2 of the parents have 2 kids each. They don't just have 1 kid to watch. They have to watch 2 kids. And if you have to watch 2 kids at the same time at the playground, one of these kids has an opportunity to get a little bit further away from you than you might like. And that's because you're not able to watch both kids at the same time. So a cation gets smaller because more protons than the electrons. And so I'm getting rid of an entire energy level. And I have, in this case, 3 pluses only watching 2 kids. And that means I can really pull those kids in close. So I've got a higher effective nuclear charge than my negatives. Whereas, and I also lose an energy level. Whereas my anion is going to get larger in size because more electrons than protons. I've got 10 electrons to keep track of, and I only have 8 protons. So the electrons are able to spread out further. They're able to get a little further away because you don't have as much protons pulling you in. So the increase in electrons overcomes the nuclear attraction in the element. So a sodium atom compared to a sodium ion. Remember, when I gave away this one electron and it went off into well, generally it's being donated to another element, but when it goes off to this other element, it leaves behind an ion that has one less energy level. So a sodium atom is larger than a sodium ion. So it loses an electron, and the positive cation is smaller because they lose an entire energy level. For an anion, this is a chlorine atom, so a chlorine that has no charge, and a chloride ion that has a Cl-1 charge. So in the inside of my nucleus here of chlorine, I have 17 pluses. And in my nucleus out here, my energy levels, I have 17 minuses. But in my ion, I only have 17 pluses, but I have 18 minuses. I have more electrons than I have protons, and those electrons are able to get a little bit further away from me because the negative anions get larger because they're adding an electron to the outermost energy level, and it makes it to where the nucleus cannot pull the electrons in as closely. So ionic sizes decrease as you go across a period. Hey, wait a minute. That's the same trend that we were when we were an atom. So that's good because that's the exact same trend. However, you just have to know the difference between what happens to cations and what happens to anions. So lithium is going to be a cation, and then also beryllium is going to be a cation, and boron is going to be a cation when it creates one, and carbon could create a cation too. And so as I go across to the right, this one's only going to lose one electron. Just one electron is going to go away. And this one's going to lose 2 electrons, so it's even getting smaller yet. And this one's going to lose 3 electrons, and so it's going to even be smaller yet. So as I lose more and more electrons, I get smaller and smaller as I go across in my cations. But the same thing happens with anions too. So the anions keep getting smaller as I go across as well, because I keep gaining more and more electrons. So phosphorus is going to gain 3 electrons. It has a -3 charge. So it gained 3 electrons, whereas sulfur only gained 2 electrons, and chlorine only gained 1 electron. So it was bigger and then a little bit less and a little bit less. So it is still going smaller to the right because this one gained in 3 electrons, that one gained in 2 electrons, that one gained in only 1 electron. But it still decreases as I go to the right. So more protons every time makes me have a higher nuclear effective charge, a higher effective nuclear charge. It increases as it goes down a group because of those extra energy levels that I get. Each time I go down, I'm going to gain another energy level. So I'm going to still have the same circumstances as I had with my electrons, because if I'm in the same group going up and down, it does mean that I give away the same number. Remember, valence electrons are the same for each of the families. So in the first column, I have 1 valence electron, and that's true of everybody in the first column. But every time I go down, I gain another energy level. So as I go down the families, I'm going to gain another energy level every time. And as I'll lose the outermost electron every time. And so I'm still going to be getting larger as I go down because I keep gaining another energy level each time I go down. And I'm also having more and more shielding electrons. So shielding electrons, remember, are the electrons in the inner energy levels that block your nucleus from being stronger. And you get that every time you go down and get another energy level. So in a nutshell, it increases an ionic size as I go down, and it decreases for the cation as I go to the right, and it decreases for the anion as I go to the right. Now, I made two different things here because we have different kinds of ions here. So remember, positive ions are when you lose electrons, and negative ions are when you gain electrons. So I had two different ions to talk about, but the trend is the same. It decreases as you go to the right, and it increases as you go down. The reasons are always the same. As you go to the right, the reason that anything happens as you go to the right is because you gain more protons as you go across to the right, but you don't gain any more energy levels. The reason stuff happens, which is increasing as you go down, is because I gain more energy levels. Every time I go down, I gain another energy level. And every time I gain another energy level, I gain more shielding electrons. So the reason why what happens is the same for both atoms and ions. So here's some general pictures of showing you relative size of your ionic radiuses. And so this is elements that are lithium, beryllium, oxygen, and fluorine. So you're looking at the same period. You're looking at period 2 on the periodic table going across. This is what lithium's ion looks like. This is beryllium's ion. Lithium is a +1 ion. It gave away 1 of its electrons. It still has the same number of energy levels as beryllium, so it doesn't have any different number of energy levels, but beryllium has another proton. So lithium only has a +3 center, and it's got 2 electrons. But beryllium has a +4 center with those same 2 electrons. So it's able to pull them in closer, as you can see in this illustration. So it is decreasing as you go to the right. Oxygen still is in energy level 2. It still only has 2 energy levels. However, oxygen has 8 protons in its nucleus. And instead of having as an anion, because this is ionic, and as an anion, it has 10 electrons. Okay, so it's got 10 electrons to the 8 protons, whereas fluorine has a tighter nucleus because it's got 9 protons and it still has 10 electrons. It has 9 protons and 10 electrons, so it's able to pull those electrons into the nucleus tighter because its nucleus has 1 more proton in it. So as I go to the right, I get smaller. So you can see I'm getting smaller to the right. I'm also over here in the anions getting smaller to the right. Okay, so they get smaller to the right. But you'll also notice these are the same periods. The girls are fatter than the boys. So when girls get married, I say they get fatter because they're pregnant, they're getting ready to have a baby. So when the two elements, when they create an ion, an anion, that's when they're getting ready to make a compound. When they're in an anion, they're larger than the elements that are cations. So if they give you 2, you got to be careful because the trend for atoms would be smaller to the right. And if I look up oxygen on the periodic table, it's further to the right than beryllium. If we were talking about atoms, oxygen would be smaller. But we're talking about comparing 2 different kinds of ions, a positive ion to a negative ion. And a negative ion in the same period, that's going across the periodic table, is going to be larger than a positive ion in that same period. So, in summary, the size of an atom and the size of an ion both have the same trend. It increases as you go down, and it decreases as you go across. That's true for both atoms and ions. It's all about the opposites here on the arrow, so pay attention. So it's increasing as it's going down, it's decreasing as it's going to the right. So the summary of the reasons, every time you ask something about going to the right, it is, as you go across, more protons is the reason, because you're getting a higher effective nuclear charge. And anytime you're asking about something going down, the answer is more energy levels. And that's contributing to your bigger size, and more shielding electrons, which is contributing to the powerful force of the nucleus to be minimized by the electrons in the individual extra energy levels. So remember, the shielding electrons are the electrons that are in the energy levels that are between the nucleus and the electron in the outermost energy level. So your nucleus in the center here is being shielded by the electrons in the energy levels that are before it. So this is obviously hard to do in a digital learning environment, but say out loud just one thing that you learned about atomic size, or the trend of atomic size. And then give me an indicator in the chat of where you are on talking about the trend for atomic size. Do you know that it gets smaller to the right and larger as it goes down? And do you know why? And then do the same thing for ionic. Remember, they get separately two different trends. Cations and anions both get smaller to the right and larger as you go down. So indicate in the chat where you feel you are on the ionic trend size. Let's give a set of examples. So which is larger, a lithium ion or a carbon ion? How did I know it was a C+4 ion? Because it said carbon, not carbide. So both of these are the same kind of ion. So it's getting smaller as I go to the right, means lithium is going to be larger. Sodium ion or a potassium ion? Sodium ion or a potassium ion? They're both in the same up and down group. So they get larger as they go down, because sodium has 2 energy levels. Sorry, it has 3 energy levels. And potassium has 4 energy levels. So it's going to be potassium that is larger. Who's larger, a boron ion or a beryllium ion? Find out where they are. They're in the same period going across. Beryllium is here, boron is here, relatively speaking. So who's going to be larger? Remember, it gets smaller to the right, so beryllium is going to be larger. Bromide or fluoride, these are both negative ions. So you're comparing two different negative ions. So go find out where bromide and fluoride are. So fluoride is up here and bromide is down here. They are in the same group. So fluoride has 2 energy levels and bromide has 4 energy levels. So who's going to be larger? Bromide. That should say bromide. IDE. That's a typo. That's IDE. Nitride or phosphide. Nitride or phosphide. So go find them. They are in the same up and down group. Nitride's here, phosphide's directly under it. So you get larger as you go down. So that's phosphide. A boron ion or a nitride ion. Look to see where they are on the periodic table. So boron is a +3 ion, and nitride is a -3 ion. And although each of these get smaller as I go to the right, you would think that it at first glance would be boron because of its location on the periodic table. It's closer to the left. However, boron is going to lose an entire energy level in the process of making an ion. It's going from having its 5 protons and having 2 energy levels down to, it has 3 electrons in this outermost energy level. And when it creates its ion, it loses this outer energy level and the electrons that are in it. So it's going to look like this. Whereas when I have a nitride ion and it creates it's going to have its 7 protons in its nucleus, but it's still going to get to keep its 2 energy levels because it not only has the 7 electrons that it started with, but it gained 3 more electrons when it became an ion, and so it's not losing any energy levels. So the boron is going to be smaller by a lot. It loses an entire energy level. So nitride is bigger, much bigger, because it is comparing a negative ion to a positive ion. And negative ions are larger than positive ions in their same period. Okay, so boron makes a positive ion and nitride makes a negative ion. So it does matter which kind of ion you create. Remember, that's a typo. That's a D. All right.